Hi everyone, this is Tasaki. In this webinar, I'd like to discuss my recent work with my longtime friend Raphael Lefevere. And it's about the hierarchical Lorentz mirror model. And this is the East Asian expression of the date, and it says 2026, February the 3rd. I think this is a perfect day to talk about our universal two-thirds law. And this is Raphael through the looking glass. Right, so our main topic is normal transport. Okay, I think many of you know about this. So suppose that here is a sample which has cross-section area A and the length L. And you place this sample in between two particle baths with different particle densities. And then in the steady state, there will be particle current J. And this current must be proportional to the difference in the densities. And here's the proportionality constant, which is called the conductance. Okay. And the normal transport means that the conductance, as usual, is proportional to the cross-section area and inversely proportional to the length. Okay. And if you assume, in this case, fixed low, if you assume some diffusive low, then this, of course, normal transport can be derived easily, okay, rather trivially. But we ask whether we can get normal transport without diffusion. So the question is, do we get normal transport from fully deterministic and non-chaotic dynamics of course we need something, in a quenched random environment. And an ideal setting to study this kind of question is the Lorenz class, especially its discrete version of called the Lorentz mirror model, introduced by Recursion and Cohen back in 1988. Okay, so that was the most basic introduction, and here's the content. Okay, and although we are mathematical physicists, our mathematical part is only this main theorem and appendix. Okay, and I will have a long introduction about the original Lorentz mirror model. All right, so let's consider the Lorentz mirror model in dimension 2. Okay, and I consider L by L square lattice. I think in this case L is 6. And I take open boundary condition in this direction. So this side is open, and periodic boundary condition in the vertical direction. So this and this are the same, right? This and this are the same, usual periodic boundary condition. And then at this open side, we add L external edges, 6 edges here and 6 edges here. And they are called external edges. All right, we do transport between these two edges. Okay, and then, oops, I forgot to say this. So this is a rather unusual setting. You have periodic boundary condition in this direction and open here. But this particular geometry is suited for the study of transport phenomena. And as far as I know, this geometry was introduced by Raphael back in 2015. Okay, and now we do this. Okay, so at each vertex independently, we choose one of the 3 configuration. With probability 1/3, you don't do anything, and you put with probability 1/3, you replace mirror like this, or you place mirror like this. So let's do that. Okay, so you get this random configuration of mirrors. If you get it, then you fix this configuration. This is our quenched random environment. And then, of course, we assume that a particle or light ray is reflected by mirrors. Okay, that's of course usual. And let's try injecting a particle or light from here. Okay, here. Of course, this is reflected, so Alice goes in and reflected by the mirror. And remember that we have periodic boundary condition. It appears here, and then she comes out. She comes out from this. And so she goes in and comes out. Okay. And one thing I want to note is that in this case, trajectory is reversible. Okay, so this was the trajectory, but why don't let Alice go in the mirror from here? Okay, of course, it's reflected like this, and okay. And this is perfectly reversible, and I think this is just trivial, just obvious from the definition. Right. And I also want to mention that the trajectory looks like a random walk. So don't we try injecting a particle or light from here, okay? And then it goes like this, and it's really like a random walk. And it's really true. Suppose that you don't know the environment, and you only discover when the light visit or Alice visits each vertex. Then you discover it's nothing, you discover it's nothing. You discover that here's a mirror, so you make this right turn, left turn, right turn, and you go like this. Okay, so this is really a random walk. And it actually doesn't turn around and go back. So this is something called non-backtracking random walk. But in this case, this is perfectly a trajectory of a backtracking random walk. And then it looks like the problem is simple, but no. I want to stress that it looks like a random walk, but it has a strong memory. Well, to see this, why don't we put light here? Okay. And then it goes like this and does this non-backtracking random walk motion, but here it comes back to the same position. Now the environment is quenched. Okay, and it knows that here's a mirror already. Then there's nothing random here, and it must be, there's no choice, and it must be reflected like this. And it goes on like this randomly, and then again comes here, then no choice, so it is reflected like this. Again, no choice here, no choice here, and anyway, Alice gets into the mirror and comes out in the other, onto the other side. Okay, so there is a strong memory effect, and because of this memory effect, there are many loops inside. For example, if you start from here and then you are trapped in this loop forever, and you can never get out. And you see that there are several loops, and this is not a special situation. And in general, if you have a big lattice, then there are many loops. Okay, but this is an interesting point. Although there are many loops inside, a particle injected through an external edge here must exit this system through another external edge, either on the left or on the right. Okay, so this is an interesting point. So here is a loop, but it never happens that a particle coming in from this external edge is trapped by one of these things and can never come out. That is not allowed by this reversibility. Okay, because of the reversibility, if you come from an external edge, you always go out from an external edge, either here or here. Okay, this is one of the essential points of this setting. Now, I was talking in terms of mirrors partially because of historical reason, but there is a better way of looking at these things. Okay, that is in terms of pairings. Okay, so here are three mirror configuration, but this mirror configuration is equivalent to this pairing. You pair this edge and this edge. Okay, and you pair this edge and this edge. If you have a mirror here, you pair this edge and this edge. Okay, and this edge and this edge. And the same thing for here. So this mirror configuration is equivalent to the configuration of local pairings, which look like this, right? And then it's easier to see. Now you see trajectory slows clearly. So here's the path, and this is a U-turn, and here's a loop, and so on. And our rule is, instead of mirror, for each vertex with equal probability, we choose one of the three local pairings or local matchings. Okay, just go straight, or this or this. Okay, so this is very good. And after getting this quenched random environment, what we do next is we are interested in transport, so we forget about these loops. Then only these trajectories connecting external edges remain, and we are not interested in how they are connected for the moment. Okay, so let's simplify this. The only thing interesting is, okay, this edge is paired through this path to this edge, and this edge to this edge, and then this one is after doing this paired to this one. Okay, so this is paired to this. So this quenched random environment induces a random perfect matching or pairing of external edges. Okay, there are in this case 12 external edges, and they are matched perfectly. Okay, like this. And given this perfect matching of external edges, and if you have left-right pair like this, we call it a crossing. And then we are interested in the number of crossings, and we call it C, curly C, and this is called conductance. I will come back to this later. Okay, so this was the two-dimensional case, and let's generalize this to higher dimension. So you consider a general d-dimensional L by L hypercubic lattice, and again we take open boundary condition in the horizontal direction, only one direction. So this direction here, in this direction, we take open boundary condition. So here's open, and the other d minus one direction, in case the other two directions, we take periodic boundary condition. So this edge is identified with this edge, and it's hard to see. This edge is identified with this edge, and so on. Okay. And then we do the same thing. In this open boundary, we attach external L, we add L to the d minus 1 external edges. In this case, we add 9 edges here and 9 edges here. These are external edges relevant to transport. Okay. And then we do the same thing, but we don't talk about mirrors anymore. It will be too complicated, and we only talk about local pairings. This is different from placing mirrors, okay? And so at each vertex, we independently choose one of the 2D minus 1 double factorial local pairings of the 2D incident edges. It's the same as the two-dimensional case, with equal probability. And then we have this quenched random environment and at each vertex we have one of some pairings, and then this local pairings induce random matching of the 2 times LD minus 1 external edges. Okay, right? Okay, so something happens, and again we count the number of crossings, matched pairs of left and right external edges like this, and we call this number the conductance C. In this case, you have 1, 2, 3, 4, 5 crossings. Okay, C is 5. And then when the left and right boundaries like this are exposed to particle bath with different densities, like in the introduction, then you see that the stationary current must be proportional to the number of crossings. So of course, you must go through these crossings. Okay. And so it's reasonable to call this conductance. This was discussed by Raphael and Schifodel and Lefevere, 2016. Okay, so this is the definition. And now we look at the normal transport property in this Lorentz mirror model. Okay, so C is the conductance, but it's sample-dependent quantity. So we take the sample average of this thing and get a function only of the system size L. We call this mu bar L. This is the mean conductance. Okay, and if the transport or diffusive, we would have normal transport, and it said that the conductance is proportional to A and inversely proportional to L. And in this case, A is equal to L to the d minus 1. So this says that this normal transport should be proportional to L to the d minus 2. And there are numerical and theoretical support for normal transport in the Lorentz mirror model on the cubic lattice d equals 3. And Jan Schifodel and Raphael Lefevere in 2016, they did numerical simulation, a bigger one, and really found this behavior, interestingly. And last year, Raphael published a sort of multi-scale analysis, theoretical analysis, which supports this. Okay, and this is not the simulation by Jan and Raphael, this is a much smaller simulation done by Raphael on his laptop computer. So they have much bigger data in this paper. But anyway, so we did size only up to 128. But already we clearly see this linear behavior. Because t equals 3, so this must be linear in L, and it's perfectly linear. Okay. So interestingly, we have normal transport without diffusion. So this is expected from diffusive behavior, but we got the same behavior. They got the same behavior without diffusion. No stochastic forcing, no chaos. We only have quenched random environment. Very interesting. And we have to stress that the structure of the trajectory is far from diffusive. Okay, inside there are so many loops and traps. If you start from inside, then you're almost certainly trapped. Okay, but if you go from the boundary, go in from the boundary, and then you can go through or you can come back, and you see this perfect normal transport behavior. Okay, so we want to prove this, of course, but for the moment, it seems that the rigorous proof is formidably difficult. Right, and so let's seek for a doable problem. And here we propose a tractable, yet highly non-trivial, hierarchical version of this Lorentz mirror model. All right, now we can go to the main part of hierarchical model. Okay, let me start from some sort of historical introduction, brief introduction about hierarchical model. And hierarchical model in statistical mechanics was introduced by Freeman Dyson back in 1969. And this is an introduction from paper by Blair and Sinai, also an important paper. Recently, it's not very recent, but it was recent at this time, Dyson introduced so-called hierarchical models, imitating, probably you say that there's a typo, but it was typo in the original, I copied, imitating in many respects the lattice system with parallel. So it's an easier problem than the original lattice system, but it's not as easy as mean field. Okay, it's sort of in between, right? And it's in a sense mean field-like. Interactions operate over blocks, but it still preserves the correct dimensional scaling. This is an important part. And if you know something, don't worry if you don't know anything about critical phenomena, but if you know about critical phenomena, I stress that these models predicts the correct upper critical dimension of some spin system like the Ising model, and also non-trivial critical exponents below the upper critical dimension to the leading order in the epsilon expansion. Okay, if you don't know anything, just ignore. And this is I will just show a picture of the original construction of Dyson. You start from these lattice. These are spins, I think, and first you let nearest neighbor spins interact in this way, and then you introduce smaller introduction in between these blocks and much smaller interaction between these smaller blocks and so on. Okay, but don't worry, we are going to define our hierarchical model, and I think it's easier to understand. Okay, so I will go into the definition and the recursion relation of our hierarchical model. Right. Okay. Here's the basic setting. So dimension is denoted by D. Dimension 1 is boring, but we can define the model. So we define it. 2, 3. These are the main playground of ours. And we fix a positive integer A0. Okay. And then the integer n counts the generation. It starts from the zeroth generation, and first, second, third, it increases. Okay. Now we define the generation 0 block. This is the beginning. It's very simple. It has horizontal length 1. It can be anything, but let's say it's 1. And it has A0 external edges on the left and on the right. In this case, A0 is 4. Okay. And we're going to define generation and block recursively. But anyway, its geometry is like this. Okay. The generation and block has AN external edges on the left and on the right, right? And this AN is given by this. So when generation increases, this number is multiplied by 2 to the d minus 1. And the length is, of course, 2 to the n. So when generation increases by 1, the length is doubled. Okay. Then how do you construct this? Well, we do it in a hierarchical recursive manner. Okay, so to construct generation n block, we prepare 2 to the d independent copies of generation n minus 1 blocks. Okay, and so this is the two-dimensional case. We have 1, 2, 3, 2 to the d is 4. We have 4. This is three-dimensional case. So 2 to the d minus 1 is 2 to the 2 and no, 2 to the this 2 to the 3 is 8. So you have 1, 2, 3, 4, 5, 6, 7, 8. 8 and minus 1 blocks. So as I said, we have correct dimensional scaling, right? Okay, and then but here they are not, they are disconnected. So you want to connect these edges, and this is what we do. Okay, here so this is an interfacial region. So we take a random matching of all the edges here. There are 2 to the d times a n minus 1 edges. It's equal to twice the an. And we consider just a perfect random perfect matching of all these external edges at the interface. Okay. In other words, we choose one of the 2an minus 1 double factorial perfect matchings with equal probability. Okay. So you don't care if they are close to each other. You just consider a random perfect matching of these 2 times an external edges. Here we have something me feel like. Okay. So this completes the generation n block. Okay, so now so now these are not external edges anymore. They are connected. So here we have external edges, and there are 2 to the d minus 1 times an minus 1 external edges, and it's of course equal to an, and horizontal length is of course double. So you get this. Good. So well, you repeat this many times, and this is my effort, the result of my effort of drawing the third generation block for the two-dimensional case with a0 equals 4. So here you have generation 0 block, and if you combine 4 of them to form, this is the first generation block, and this is the second generation block, and you have the third generation block. I don't want to do the fourth generation. And you clearly see that we keep correct dimensional scaling. It really looks like 2-dimension, but of course you have something weird here. So we also have mean field like long-range matching. Okay, so this is our hierarchical construction. I think it's very clear. Now I claim that we have exact recursion relation describing this model. So let P and L be the probability that there are exactly L crossing in the generation n block. So L is the conductance. Okay, and by definition we start from a 0 connection. So P0 of L is just the Kronecker delta, and I claim that this in general, for general n larger than 0, we have this recursion relation, and P and L is obtained from the product of 2 to the d independent Pn minus 1. Well, this looks very plausible, and we have this kernel, recursion kernel, and this is summed over all these crossings of the n minus 1 generation. Okay. And here in this kernel, we have this variable LL and LR, and they are defined like this. And I think it's rather obvious. We have 2 to the d minus 1 copies of the previous generation on the left. So you add the crossing on the left. So in this case, we have 2 crossings here, 4 crossing here. So this is 6. And this is, well, we add the crossings on the right. And in this case, 0 crossings, 2 crossings, so LR is 2. Okay. So anyway, the important thing in this kernel, you only see this LL and LR. These are the number of crossings on the left and on the right. Good. So these are LL and LR. And what is this K? Well, this is just the kernel for this recursion relation, but this can be interpreted as the conditional probability that there are exactly L crossings between the leftmost and rightmost sides in this n generation n block after random matching. So we want to compute this conditional probability. Okay, this probability comes from this random choice of matching at this interface. Right, so what we have to do is, given this situation that there are LL crossings on the left and LR crossings on the right, and we have to do random perfect matching of all these twice 2 times AN edges. In this case, we have 16 edges, and we have to consider 2 million ways of matching, perfect matching of these things. But I claim that this can be simplified, okay? I claim that you can forget about all these U-turns. So if you do random matching, this may be matched to this U-turn, and this is matched to this U-turn, this matched to U-turn, and again, so you have to consider all these U-turns, right? But I claim that this is actually the job is perfectly equivalent to considering random perfect matchings of only LL plus LR edges, which are the endpoints of all these crossings in the previous generation. Okay, this is not really trivial, but this is a consequence of permutation symmetry. So if you just sit down and think, and then you will understand. But for the moment, you please believe me and go on. And then the calculation is much easier. In this case, we have 1, 2, 3, 4, 5, 6, 8 edges. So we only have to consider 105 ways of random matching. Okay, and anyway, in general, it's quite easy to compute this thing now. And now you first consider the total number of matchings of LL plus LR edges, and this is, as you know, given by this. Okay, so this comes into the denominator, and then you count the ways of forming L crossings between here and here. Okay, and so first of all, you pick the candidates from the left to be connected to the right, and you also pick the candidates of L edges from the right. Okay, and then you connect them. Here the way of connecting these L things, of course. And then this is not the end of the story. Some guys are left, and they have to form new U-turns. And so these are the ways to form U-turns. Okay, so we have this exact expression. So for this is a summary. We have this exact recursion relation. This is a probability that there are exactly L crossing. L is the conductivity. No, conductance. L crossings in the generation n block, and it satisfies this initial condition and this exact recursion formula with this recursion kernel. And this is the conditional probability, so of course it satisfies this normalization condition. All right? Okay, so now let's go to the next part, and we discuss our main theorem on normal transport. But in this part, I only have 2 slides. The first slide is very sloppy. This is very physicist. Okay, right. So we are interested in conductance L, but it's sample dependent. So we take average of this mu n. Yes, okay. Did I say it correctly? Yes. So yeah, I take average. Anyway, I take average of this L, and this is a mean conductance. Yes. Okay, so this is the sample average of everything, and this is the mean conductance we are interested in. Okay, but it's also important to consider conditional mean. That is, given that there are LL crossing on the left and LR all crossing on the right, and look at the average expectation value of L. Okay, and since we know this explicit form of K, we can actually compute this exactly. And this is just an easy exercise, and you get this. And when LL and LR, the number of crossings in the previous generations, are large, then you can ignore this 1. And then this becomes this simple, familiar expression. And in this case, this is something really familiar, because L is basically conductance. So its inverse is resistance. Okay? So you are simply adding 2 resistance. So this is, if you have 2 resistance in series, then you simply add them. So yeah, you see this. Okay. Now let's be sloppy. Okay, so this is our exact recursion formula, but suppose that this P has a sharp peak somewhere, and then you can replace this L by just the value at the peak. And of course, the value at the peak should be mu of n minus 1, okay, this average. So in the crudest approximation, we can simply replace L here by mu n minus 1. Okay, and then LL is just the sum of 2 to the d minus 1 LJ, so it's almost equal to the 2 to the d minus 1 times mu n minus 1, the average from the previous generation. Okay, the same thing for LR. So we simply plug this in here and just do a careful calculation, and it's easy, but you have to be careful. You put this and add and inverse, and anyway, the result is this. Okay, you see that this mu n, the mean conductance in the nth generation is 2 to the d minus 2 times the mean conductance in the previous generation. Okay, this recursion is so easy to solve, and you get this. And if you recall that this mu0 is equal to a0, this is this, and you can rewrite in this familiar form. The mean conductance is almost equal to the area, cross-section area, divided by the length. Okay, if you recall this. So we have normal transport. Okay, of course, this is a very sloppy argument. We replaced L by its most probable value. But we can basically prove this. Okay, so this is our main mathematical contribution. And in dimension 3 or higher, actually 2 is tricky, 3 or higher, and for sufficiently large as 0, but I'm not saying that it must be 10 to the 10th. Actually, in dimension 3, the only condition we need is a0 is greater than or equal to 2. But we already assume that a0 is a positive even integer. So actually, there's no condition for d equals 3. There are some conditions for higher, but it's nothing like 10 to the 10th. Okay, so basically, this. If you're interested in 3-dimension, I am, and then there's no assumption on the a0. And there exists positive constant CD and C prime D in 3-dimension case. They are like this, and we can upper bound mu mean conductance by this, and lower bound mean conductance by this. We have -1, but if this becomes, of course, this gets large, so this -1 is nothing. Okay. So upper bound is rather easy. Lower bound is harder. But I mean, the proof I will explain is rather soft, and it can be written in like 2 pages. Okay. Anyway, we can prove this upper and lower bound for all n. And if a0 is large, then these C and C prime are almost 1, and then this inequality reduces to this estimate, which we got from this very crude assumption. Okay, so in short, we proved normal transport by only using non-chaotic deterministic motion in a quenched random environment. No stochastic forcing, no chaos, no nothing. But we have this normal transport expected from diffusive law. Again, we have no diffusion. There are many loops inside, as in the original model. Okay, this is a side remark. I said we also define the model for the boring case d equal 1. And in this case, if you assume also d equal 1 is just this kind, and you can solve it in different ways. But anyway, so this is a generation 0 block, and you simply just connect this generation L block in this way. Okay, and so in this case, you must make a0. In this case, a0 is not large, but you must make a0 very large to observe something non-trivial. But then if a0 is taken to be very large, and then we again have this normal transport like scaling, as long as this mu n is larger than order 1. And this is very easy to prove. Okay, all right, so that's our main theorem. And so after discussing this mathematical theorem, and I'm talking about the idea of proofs in the appendix, and again, I only have basically two slides here. Okay, but But before that, or before anything, let's be physicists again and consider a rather plausible approximation for this problem. Okay, so P and L, again, is the probability that there are exactly L crossings in generation n block. Okay, and we are interested in this mean conductance. And we are also interested in this sample-to-sample variance of the conductance. L is bare conductance, but of course it fluctuates between samples. So this is the sample-to-sample variance. And then it is, physically speaking, it's rather plausible to assume that this Pn is approximated by a Gaussian with mean mu_n and variance Vn. Okay, and if we do numerics, this is a numerical results for three-dimensional hierarchical model with a 0 equal 2. Okay, and we standardized this P and L and compared it with the Gaussian distribution for these values of n. Okay, and first of all, this is a Kronecker delta, so it's very far from Gaussian, but this is 2, 3, 4. When n equal 5, it's almost indistinguishable, or n equal 10, it's perfectly Gaussian. So this ansatz is very plausible, but of course this is very non-trivial. So we want to prove this, and we still cannot prove it. But anyway, we make this ansatz. Okay. The second thing is approximation of this kernel. So we have this exact expression for the kernel, and then you're not surprised if I say that this is approximated by Gaussian. And we already said that we can compute this conditional expectation. We can also compute this conditional variance. Okay, so we can approximate this by Gaussian, or you can use like Stirling formula, and you can make this rigorous in some limiting situation. Okay, so we have this ansatz, plausible but non-trivial, and we have this approximation which can be justified. Okay, and then we recalled that we have this exact recursion formula. So we use this ansatz. This is okay. Then this is Gaussian, and this is Gaussian, and you can of course replace this sum by integral. Then you just do complicated Gaussian integral, and mathematician can do it for you, and then you get this form, and you can write this mu_n and Vn in terms of everything you have here. Okay, and in dimension 3 or higher, the leading terms of recursion for mu_n and Vn you get look like this. Okay, so let's examine this. So I think you understood what we did. What we did was just a Gaussian integral. Okay, and all these saddle point approximation and so on. So let's, okay, so first of all, we got this one, but we already knew this. I mean, we already saw this in the crudest approximation. And if you solve, but we are claiming that this is true for only for large enough n. Oh, okay, I had to say that this Gaussian ansatz is for sufficiently large n. So we expect that mu_n behaves like this, with some constant, so you can rewrite this in this way. So here's the conductivity, but this is a non-universal constant. But anyway, this is what we expect. And actually, we have proven this rigorously as an upper bound and lower bound. But anyway, numerics is easy. So if we do numerics for three-dimensional hierarchical model with this geometry for a 0 equal 2, and then if you plot log base 2 of mu_n, then versus n, then you get this slope 1. So you confirm this. And if you divide mu_n by 2 to the n, and then you get this convergence. This is not the best fit, but anyway, this converges to constant. And in this case, kappa conductivity is 1.1, but this doesn't mean anything. Okay, right. Okay, what about the recursion for Vn? Okay, so this is new. And it's interesting that this only contains one term, but this contains two terms. And this is sort of essential. And first of all, this one is sort of natural. This comes from the fluctuation from the previous generation. Of course, you're fluctuating in the previous generation. So of course, it comes to your generation. But here's another term. This is a fluctuation coming from random perfect matching that happens in this orange plane. Okay, we do this. So this comes from sort of previous scale, and this comes when you grade up your scale to the higher version, and there comes extra connection. Okay. Anyway, you have two terms. Okay. But why don't we divide this by this thing? Okay. And then very nice thing happens. Mu is here and v is here. So you get a recursion equation, closed recursion equation for v over mu. It's very simple. And also, rather surprisingly, it's independent of the dimension d, right? And this recursion relation, which we expect to hold for sufficiently large n, can be solved very easily. I think a high school student can solve this. And the solution is that v over mu converges rapidly to 2/3 as n grows. We are in dimension 3 or higher. Okay. And this is, again, numerical plot of this hierarchical thing. And this is generation, and you really see this quick convergence to 2/3. Okay, these are everything about dimension 3 and higher. As I said, marginal dimension is 2, and it's more tricky. Okay, and if you consider our basic recursion for the equal 2, then we had power d minus 2 here. But d minus 2 is 0 in this case. So in this case, you have to consider subleading order terms. Okay, and this is the same. And now you can solve them. You have to now couple them and solve. But if you solve it, then you find that this mu n is not constant. Okay, normal transport says that mu is constant. Normal transport says L mu is proportional to L to the power d minus 2. So in this case, mu should be constant if we believe in this naive normal transport. But in this case, it grows slowly, linearly in the number of generation. In the language of length of the system, it's logL. Okay, so we see weakly anomalous transport with a logarithmic correction, but you're not surprised because we are in the marginal dimension. Okay, and again, if you solve this for Vn, then what you get is n over 18, and again you see that this ratio v over mu converges to 2/3. So we again see this 2/3 law, today's state, and okay, this is numerics for the equal to hierarchical model with a0 equals 90. It's very large, but I will explain you why we did this. And anyway, in this case, this is mu versus n, nothing like log. And this is not a linear fit. We have this data points here, but I mean, it simply looks like a straight line, and we have slope 1 over 12. And this is n to 1,000, and this is n from 1 to 100 and 0 to 100. And now in this case, you have very quick convergence to 2/3 again. So, okay. So, okay, yeah, of course we have to confirm, but because these are just Gaussian approximation. But anyway, Gaussian approximation is perfectly, yes, seen. The result of Gaussian approximation is perfectly seen in this numerical result. Okay. And well, I took 90 here, but I will explain why I did that. Okay, and here are figures that we don't show in our paper, but I like this. Okay, so the reason that I took a0 to 90 is that if you take a0 equal 2 in dimension 2, we did take a0 equal 2 in 3 dimensions. That was okay. But in 2 dimension, as I said, the mean conductance grows very slowly, linearly in n. Okay, so if you take a0 equal 2, then mu is of order 10, or much smaller. Yeah, of order something 5 or 6, even if n is 30. Okay, it grows very slowly. I think it's of order 10 when n equals 100. That means, our distribution can never be Gaussian. It's very discrete. Okay, so that's why we took a0 to be 90. In that case, it's much better. It becomes smooth quickly. All right, so this is pretty bad histogram of our Pn. if we take A0 equal 2. So they are very far from Gauss. But look, if you plot V over mu for this data, this very quickly converges to 2/3. Okay, it converges to 2/3 even when n equals 10, where our distribution is something like this. I mean, it takes non-negligible values only for, I think, 1, 2, 3, 4, 5, 6, 7 values of L. So it's very, very shaky, but it's almost 2/3. In this case, if n equals 30, it's here. So it already converged a long time ago, but it's still very far from Gaussian. Okay, so this is just a numerical observation, and I don't know if this is really important or not. But we could say that this 2/3 law may be much more robust than the Gaussianity. Okay, that was a surprise to us. Okay, so this was everything that I wanted to say about our hierarchical model. So let's go back to the original Lorentz mirror model on the cubic lattice. And we cannot do any mathematics here, so let's do some numerics. And rather preliminary numerics on laptop computer of Raphael. Okay, so we did, actually Raphael did Monte Carlo simulation of the original Lorentz mirror model on the cubic lattice. Okay, no hierarchical construction. We have usual cubic lattice on which the size is L by L by L, and we took L to be 2 to the n from n running from 1 to 7. Okay, there's no meaning in here, but it's okay. It's just typical. And what we did was we generated 6 times 10 to the 5th independent random environments. So that means at each vertex, we choose one of the 15 possible pairings of these incident edges. Okay, and you get many, many, many samples. For each realization of environment, you get one environment. We faithfully count the number of crossings C. So we just calculate the number of C, compute the number of C. This is the conductance. And then by repeating this for each size 6 times 10 to the 5th time, we can estimate mu bar, the mean conductance, and also the mean sample to sample variance. Okay, defined like this. Great. Now, first of all, this mean conductance, we have already seen this. We recover normal transport. Okay. And if you want to see the larger simulation, as I said, Jan and Raphael has much bigger simulation in their paper. But already on this laptop simulation, you have this linear behavior. Okay, then what happens to V or V over mu? Okay, so we want to compute variance to mean ratio for this non-hierarchical model, real model, just numerical simulation, no theory. But we were actually surprised when we saw this. We plotted V over mu against the system size, and it grows, and it seems like it's converging to some value, which is 2/3. Okay, actually it's almost exactly 2/3 here, and it's slightly away, but it's still within the 95% confidence interval. So we wanted to be honest. We show this, but anyway, it looked like 2/3, but we couldn't believe this, and we suspect that this could be some accidental coincidence. So what we did next was considered again 3-dimensional Lorentz mirror model, but with a different local pairing rule. So we took something called orthogonal rule, in which case particle never goes straight. It must always make 90 degrees turn. It's hard to explain this in 3 dimension. Let's see the case in 2 dimension. In 2-dimensional case, we had 3 local pairings, and we took 3 of them. We allowed 3 of them. But in this orthogonal rule, we don't allow this. Okay, so in the language of mirror in 2 dimension, we always place mirror. Okay, and okay, in 3-dimensional case, we just don't allow particle to go straight. Then there are 8 orthogonal pairings at each vertex. So we choose one of the 8 randomly to construct our environment. Again, 6 times 10 to the 5th environments, and count the number of crossings, and I estimate I have to hurry up, but anyway, yes, this is a result. Okay, so this is totally different rule, so the conductivity must be different, but this is the plot of V over mu. Okay, and it does something strange, but anyway, it looks, again, it's almost 2/3 when L is 64, but when L is 128, it's still very close to 2/3. Okay. So, of course, this is just a preliminary numerics, and if you're numerical pro, I think you can do the bigger size quickly. So please do that, and I'm sure that it's still on 2/3. So I think it's fair to say that we found something. So here is our proposal, the universal 2/3 law. Okay, we observed that sample-to-sample variance of conductance divided by mean conductance converges to 2/3 when mean conductance grows. Okay, this is observed theoretically in the hierarchical Lorentz mirror model in dimension 2 or higher. It's not in 1, but in dimension 2 or higher, where mean conductance grows. Oh, but we have not proved this yet, and of course we want to prove this. Yes, but probably we can report that in our coming papers. But anyway, this must be hard. Okay, and no theory at all, no mathematics, no theoretical physics, but we numerically observed this in the original Lorentz mirror model in dimension 3. Okay, so we want to make a conjecture. V over mu, as mu grows, is a universal amplitude ratio. Probably I must explain. I think many of you are familiar with the universality of critical exponents in critical phenomena. Okay, if a critical phenomenon happens, critical exponents are universal in the sense that they are very robust. They don't change even if you change details of the model. Okay, it only depends on the basic symmetry of like spin and the dimensionality and things like that. But these are critical exponents. Okay, so but in our case, this is not exponent. These are the ratio of variance and conductance. But in some case, this kind of ratio, dimensionless ratio of some amplitude can be universal. It also happens in critical phenomena too. So we propose that this V, this ratio, is a universal amplitude ratio, and this value 2/3, 2/3, signifies a universality class of a system, including ours, exhibiting normal transport induced by random matching of conserved current. Okay, so we are sure that our hierarchical model and also the original Lorentz mirror model, at least in 3 dimensions, belongs to this universality class. So the very interesting physics question is what models belong to this universality class? An exciting question is are there any models in the continuum, as in the original Lorentz gas, that belongs to this universality class? Okay, so we're coming close to the end. We have appendix. We only have 2 slides and where I discuss the idea of the proof, but probably some of you are not interested in the idea of the proof. So let me summarize the talk first. Okay, first of all, the Lorentz mirror model, both for the original one and for our hierarchical model, provides a plane setting to study transport generated by quenched random environment. And in the hierarchical version, we prove that there's normal transport in dimension 3 or higher, and showed, but didn't prove, that we have weakly anomalous transport with log correction in dimension 2. But we stressed that we have rigorous example of normal transport, diffusive-like transport without diffusion. No noise, no chaos. We only have quenched random environment. Lots of loops, lots of traps inside. Okay, and for the original model, normal transport has been expected in dimension 3 or higher in the previous result by Jan and Raphael. But here we conjecture weakly anomalous transport with log correction in dimension 2. And with Raphael's laptop simulation, we cannot do this. But probably you, if you are numerical pro, then you can do this. So yes, please do that. Okay, and I think physically speaking, mathematically speaking, this proof is our main contribution. But physically, the most important discovery is this two-thirds law. And we discovered that the two-thirds law for the variance-to-mean ratio of conductance. And we propose that this is a signature of universality class of normal transport induced by random current matching. Okay, so that's basically all I wanted to say, except for the idea of the proofs. So if you're not watching the appendix, then okay, goodbye, and I hope to see you later. And if you are interested in, the idea is interesting. So if you're interested in appendix, a brief idea of the proof, okay, please remain here, right? So I said I have 2 slides, but I have 3 slides. But the first slide is just the slide I already shown. So this is our main theorem, okay? So I'm going to prove this upper bound, and I will show you the idea of how we prove this lower bound, okay? And I can prove this dimensional 1. We proved this, okay? First, I start from the upper bound, and this is actually easy. So this is a mean conductance that we want to control, and this is our exact recursion relation. So we simply plug this recursion relation in here, definition, and then you get this. Oh, and we switch the order of sum that is allowed. Of course, everything is finite. And then here you see something already familiar to you. This is a conditional mean, okay? Which is a function of LL and LR, and you can compute this. Okay? And then you can easily show that this is upper bounded by this. Very nice. Then you can plug this in here to get an upper bound. And moreover, since LL is simply, okay, the sum of LJ on the left and LR is the sum of LJ on the right, LL plus LR is nothing but this guy here, the sum of everything, okay? So you divide this by 4 and 1/3, and now all these subblocks are independent. I mean, subblocks are not sort of independent here, but they interact with each other here in this kernel. But after this inequality, they are just independent, and this is trivial. This L, the expectation value of L is mu n minus 1, so you get this recursion inequality, okay? And then you can rewrite this inequality in this form with this constant, and then you can easily use this n times to get this upper bound. Great. Okay, and this applies, okay, but you can do this only when this is not 1. Okay, so when d is 3 or higher, or when d equal 1, you can do this, and you get this. So we proved upper bound for d 3 or higher, and or d equal 1 by this. Quite easy. And it is interesting to observe what happens when d equal 2. In d equal 2, this becomes 1, and you have plus 1/3. So this is the easiest recursion you can solve, and the result is this. So in this case, we have upper bound of mu that grows linearly in n, and this is consistent with our log correction. Okay, we don't recover this 12, but anyway, this is consistent with log correction. Okay, so this is not a bad news. But unfortunately, we don't have any lower bound corresponding to this. Okay, so the upper bound was so easy, and probably this means that lower bound is harder. That was true. We did upper bound quickly, and then we spent a long time doing lower bound. Okay, but it turned out that we can use rather similar philosophy. Okay, now we found that it's useful to consider the mean of the inverse, but 1 over L behaves badly at L equals 0, so we consider 1 over L plus 1 and take the average of the thing and call this eta. Of course, this is the inverse of mu. Why not eta? Okay, and we also define this thing, but I will come back to this later. Okay, now we have mean of inverse, and we are interested in the mean. And in this case, very fortunately, Jensen's inequality helps us. And Jensen tells you that mu n is lower bounded by this. This means that if you can upper bound eta, then we get a lower bound for mu. Good news. Upper bound is usually easy. Okay. Now, this is our exact recursion, so we do the same thing. We plug this in to this expression of eta here, and you get this exact expression for eta n. Okay, and again we change the order of sum, and here we have conditional expectation value, which we should call eta tilde. And again, we can exactly evaluate this. And rather interestingly, this can be rewritten in this form. Okay. And now, if you plug this, so this is identity. If you plug this identity in here, and then this LL plus 1 depends only on the left half, and this one only on the left hand, and this. And then by looking at this, you will find this exact recursive identity, not inequality, where U is defined in this way. Okay. Now you see that here, this is a bit strange. You have half of them. Okay. So we used only the left half, or the same thing for the right half. And okay, this is not difficult. So by plugging in this into here, you get this recursive identity. But we expressed eta in terms of U. So this is not yet a closed recursion for eta. We want to have an upper bound for eta. All right, let's do the boring case, d equal 1. If you look at d equal 1, then d minus 1 happens to be 0, so 2 to the 0 happens to be 1. So in this case, you don't sum this at all, so U is the same as eta. Very good news. In one dimension, this is eta. And then you can throw this away to get an upper bound, saying eta n is less than or equal to twice the eta n minus 1. Okay, and this is again very easy recursive inequality to solve, and you get this. And if you recall that eta 0 is 1 over a0 plus 1, you get this upper bound for eta n, and by using Jensen, you get this lower bound for one-dimensional case. And as I said, one-dimensional case is boring, but this is a good exercise that you can lower bound mu n with the physically correct scaling. Okay, now in dimension 3 or higher, you have to relate U to eta by using further clever concavity argument, and that is not trivial. And I won't explain that in this webinar, but it's not like 10 pages proof. It's within like 1 page or less. Okay, and it's a clever concavity argument. And I want to say that this concavity argument was found with the help of ChatGPT 5.2 Pro. Okay, so we gave all these beautiful ideas and suggested and asked if it can prove this, and it finally came out with this clever argument. It was very nice collaboration. But I warn you that before this, ChatGPT produced many proofs, perfectly rigorous, consistent proofs of this inequality, this inequality, this inequality, which turned out to be totally wrong. Okay, we had to go through these proofs each time whenever ChatGPT produced it, and we have to find some mistake and ask it, and so we had to do that. And of course we had to plug in some beautiful ideas like this and this and this, and to let it do the proof. And of course we finally had to check and improve and rewrite the proof. Okay, so that is the status in 2026, February the 3rd. Okay, of course you belong in the future, so probably the situation will be different, but at this stage, okay, don't believe these guys too much. Okay, you have to do your work. I think that's a nice part. Okay, so that's really what I wanted to say in this webinar. Thank you very much for watching. This is the summary slides you have already seen. Oh, and I forgot to say that there are so many things to do numerically, theoretically, and mathematically. Okay, thank you very much for watching, and goodbye.